In this video, I want to think carefully about one idea, the multivariable chain rule. By the end, I hope this idea feels simpler and more connected. So, in single variable calculus, the chain rule is just simple. As you may have learned, if you're given a function y equals f of, let's say, g of x, then the derivative of y, we need to apply the chain rule, right? So the chain rule is the derivative of f prime of g of x times the derivative of g. So this is the chain rule in single variable calculus. For example, let's say we're given a function y equals e to the sine of x. Then what's the derivative of this function? We know that we need to apply the chain rule. So y prime is just equal to the derivative of the outer function, which is e, which is still the same. So still e. The inner function stays the same, and times the derivative of sine is just cosine. So, cosine of x, and this is the derivative of y when it is e to the sine of x. All right. Now let's talk about the same rule, the chain rule, but in multivariable space. All right. Before we get into the chain rule in multivariable situation, I forgot to mention just one thing. So the intuition of this formula is that the total rate of change of y with respect to x. In this case, when we need to apply the chain rule, it comes from the rate of change of y with g of x and the rate of change of g of x with x. So that's the flow of the chain rule when the function has an outer function and inner function. In multivariable calculus, in multivariable situation, let's say we are given a function, a multivariable function z, which is f of x and y, and each component, both x and y, are functions of t, where t is just a variable. Then the chain rule, in this case, the chain rule of z, the derivative of z over t dt with respect to t is equal to partial x of xy times dx dt plus partial y times dy dt. So more visually, I can rewrite this as, so the chain rule in multivariable calculus is, so dz dt is partial z with respect to x times dx dt plus partial z with respect to y times dy dt. And this is the mathematical formula of the chain rule in multivariable space. And now let's talk about the intuition, like how we get this final equation, why this is the formula when there's a dependence in functions. Now I want to show you an informal justification showing how we get this multivariable chain rule formula. So let's say we have a tangent plane to the function z at a point, let's say AB. So let's say there's a tangent plane, to function z, sorry, f of xy, this is x and y, at a point A, B. In the previous video, we learned the equation of the tangent plane, right? So the equation is z minus z naught is partial x of AB times x minus x naught plus partial y of AB times y minus y naught, where z naught is just the function at the point AB. So we got this equation, and let's say for the origin, for the function, sorry, for the point, x, y, and z near the point x naught, y naught, z naught, the change in x naught, y naught, z naught, the difference between these points is just x naught minus x, y naught minus y, z naught minus z, right? Sorry, it's the opposite order. So x minus x naught, y minus y naught, z minus z naught. And that's just, we can express this as just delta, using delta sign. So this is delta x, delta y, delta z. This is just equal to x naught, y minus y naught. Sorry, this is comma naught, z minus z naught. Do you see where we are heading to? So look at this equation and look at this delta sign. Using the orange colored pen, look at here, here, here. We can replace them using this delta x, delta y, and delta z. So rewrite this equation. Delta z is equal to partial x at the point AB times delta x plus the same for the y part, partial y of AB times delta y. All right, we got the simpler equation, right? And let's say the same equation, but for a small change in t, or small change in t, or delta t. Then we get the equation. Delta z with respect to delta t, and that's just equal to the same for partials times delta x over delta t plus partial y of AB times delta y over delta t. We are almost there. Now you see this, right? Now you see how similar we are as you see the actual formula of the chain rule. So since we are using the delta, sorry, this should be the approximate sign, not the equal sign. Now, using the limit, we can rewrite the delta sign to just d. So this entire equation can be rewrite as the final equation, the final formula. dz over dt is equal to partial x times dx dt plus partial y times dy dt using the limit. That's how we got the formula of the chain rule, and I hope this helped you the intuition behind this mathematical just formula. So far, we talked about the mathematical formula of the chain rule in multivariable space, and we just talked about the intuition behind the formula, why that is it. At this point, for me, at least for me, I was wondering a few things. I did have two questions. First, why do we add two contributions? Why do we add the x part, the partial x times dx dt, and why do we add it with partial y times dy dt? So each term tells you how one variable's change contributes to the total change in z. For example, the x part, partial x times dx dt, that's basically the part of z's change caused by how x changes with t. The logic goes the same to the y part. This part is just the same. The part of z's change caused by how y changes with the variable t. So we add them together because both effects happen at the same time. The total change of effect, the effect's change, is always the sum of all contributions. Another question was, why do we multiply partial x by dx dt? Or why do we multiply partial y by dy dt? I was wondering, why do we have to multiply them? So let's talk about the x part. The logic goes the same to the y part. So for the x part, partial x times dx dt, this is we can say in words, this is just the same as change of z over change of x times change of x over change of t, right? So this is just the total rate of change through the path, starting from t to x to eventually z. So this is the path, and the reason why we multiply them is because of how rates of change compose. So this is important. Let me give you an example. Let's say if z changes twice as fast with x, and x changes third times fast as t changes, then how fast does z change? Z changes 6 times fast with t. Do you get it? So z changes 2 times 3, which is 6 times faster, 6 times as fast with t value. So this is the logic behind the multiplication. So for the rate of change, we always multiply. So that's why we still multiply here, like the partial part times dx and dt. Today we explored the chain rule in multivariable calculus. It is important to actually understand the intuition behind the mathematical formula, because when we learn later, when we learn directional derivatives or the gradients, which is fundamental, like important part in multivariable calculus, it helps you a lot if you actually understand the logic behind the chain rule. For example, like the reason why gradient always points in the steepest hill, like why it always points the most steepest increase at that point. If you understand the chain rule, it is way natural, way better to understand. Next time we're going to we're going to talk about implicit differentiation. It's going to be very fun and interesting. So until then, let's keep things simply connected. I will see you in the next video. Thank you.